So stabilizer of 0 in G, this is a singleton 0. Hence G mod G0 is equal to R. This is discrete topology. So this therefore G mod G0 is not really homeomorphic to X. So now the thing is, so this question is, so let us use a trace space. Question: under what condition alpha is a homomorphism? Is a homeomorphism. So usually people give condition on G and condition. So we need some condition on G or X so that alpha is homomorphism. Usually people give condition on G rather than giving condition on X. This is simply because G has more structure than X. G is a topological group, or X is simply this topological space X. But there is one situation where you can really say that alpha is a homomorphism. What is that situation? See, the thing is, alpha is a X is a Hausdorff space, and alpha is a continuous map and bijective map, right? If X is a Hausdorff space, then if G mod GP is compact, then you can say that this alpha is a homomorphism. So answer, the first condition is this: whenever G mod GP is really compact. There is some theorem which you already know that this is. So, but we want some condition on G. Then therefore, whenever G is compact, so this is certainly G mod GP is compact. Therefore, this is a homomorphism. But this situation is very unlikely. So what one does that one proves the theorem like this: whenever G is sigma compact. G is sigma compact means simply it can be written as countable in any compact sets. And for the proof, you can see full and abstract harmonic. And
so you are saying when G is sigma compact, then G mod GP becomes compact, or
no, G mod GP doesn't compact, but alpha
becomes homeomorphism.
Yes. Just wait 1 second. Huh? Okay, so one very practical situation is whenever G is second countable. Also, this is really true. And this is due to this fact that simple proposition. And what does this means? G second countable means this G has a countable base. This means simply this. G second countable means that is G has countable base. Okay, so this term. There is a proposition like every second countable locally compact Hausdorff topological space is sigma compact. Okay, so you can prove this an exercise. You can prove it on your own. If you cannot do, then look at any topological book on topology. So remember this chronology. Whenever G mod GP is compact, or G is compact, or G is sigma compact, or G is second countable, then this alpha is a homomorphism. To the best of my knowledge, this is the most general situation where this alpha is an homomorphism. Okay, Now we move to Lie group setup. So in Lie group thing that we have to really replace everything by a smooth manifold and G to be Lie group. And we in that situation we demand that alpha is a diffeomorphism or that. But in the Lie group setup that we have, since the map is smooth, then group action is, since group action is smooth, you expect that you will get some better result, but you will not get better result. So this is the thing, and same counter example will work. So remember, I have told you that discrete topological groups are also Lie groups. Okay, but so this counter example will also work for Lie group setup, and there are also some non-trivial counter examples. Okay, so but I just wanted to write the theorem. So let us. So theorem in the Lie group setup. Sorry. So let G be a transitive Lie transformation group of a smooth manifold M. Manifold M. Let P belongs to M and Gp is equal to the stabilizer of P in G. So this is really G belongs to G. So that G dot P is equal to P. Assume that alpha from G mod Gp to M given by alpha of G dot Gp is really hello.
Yes, I can hear you.
Yeah,
Oh,
I
you
can
can
also
see
hear
me.
you.
Sorry. So are you able to see my screen?
Yes.
Yes. So then, okay. So then this alpha is a diffeomorphism from G mod Gp onto M. Okay. So this is for proof. You can.
Mona, I have a
Yes.
question. Maybe you have defined IISc. What is a Lie transformation group?
This simply that G acts on M transitively and the group action is smooth.
So G is a Lie group, M is a differentiable manifold, G acts on M, and the action is smooth and transitive.
Smoothly. So whatever natural maps are there, you just put smooth thing, and actually I have defined this thing. Okay, so but this is the thing. Okay, and this G acts on transitively. That's all. When G acts on M continuously, that then you call that G is a topological transformation group, and here this G is a Lie transformation group. These are just see Elgason. You can prove this. You can find this in Elgason. So this is alpha. So here you are assuming that alpha is your homeomorphism, and this happens when this G is second countable or G is sigma compact or G is compact. Okay, all those things I will come. So you just remember that G is second countable. That is a very practical situation. Okay. So now this we come back to this Riemannian manifold setup. Okay. So And so let MQ be a Riemannian manifold. Q is the Riemannian matrix. I am not taking G in manifold. And remember this IM. We have this is really a function from M to M. So that F is a diffeomorphism. And this is F star Q is equal to Q. Okay. And this is same thing as we have seen that F is a mapping from M to M. F is a bijective distance project preserving map. So F is onto F of a distance of FP FQ. Q is equal to distance of P and Q for all PQ belongs to M. So we have also seen that IM is a group under composition. Group under composition. Then which acts on M via this thing. G dot P is simply GP action of. So G belongs to IM and P belongs to M. So this is very natural action. Now I want to put a topology on IM. So what you do is this is IM. So this IM consists of all functions from M to M. So this is a function space, and the natural topology which one puts on this type of spaces is the compact open topology. So let C subset of M be compact and U subset of M be open. So you look at this WCU is F belongs to IM, so that FC is contained inside U. Okay. Now the compact open topology on. Okay, so let us write in the compact open topology on IM is the smallest topology for which this WCU is open. For which this WCU is open, and this happens for any C subset of M. Okay, for any compact C subset of M and any open U subset of M. So remember this thing that WCU C is a compact set and U subset of M is open set. WC comma U is a function from M to M, so that FC subset of U. The compact open topology on IM is the smallest topology for which this WCU is open. Okay. Now we have I will state a 2-3 theorems without proof basically, because these are proofs are 2-3 classes. If I will prove this thing. Theorem. So let M be a Riemannian manifold. Then IM. So let us see. You call this IM. IM equipped with this compact open topology. Becomes a second countable so locally compact Hausdorff topological group, which are which acts as a actually topological transformation group of M, and this just which acts as okay, which acts continuously and transitively on M. So I am not using that word topological transformation group of M. So this is a thing, and second thing is also interesting. So B is let P belongs to M. Then
Muna,
you
I
look
just
at this.
forgot. Did you show that Im acts transitively on M?
No, I have
Or
not
it is easy
shown
to
that.
see? Is it
No,
easy to see?
actually. Oh, transitively on M. Sorry. Thanks. Okay, I am really which acts continuously on M. Sorry. Thanks. Actually, Riemannian symmetric space, their action is transitive.
Yeah.
For heat Riemannian manifold case, this action may not be transitive. Okay, so that let P belongs to M. Then thanks anyway for that. Then GP, this G belongs to IM, so that G dot P is equal to P. This is the stabilizer of P in G, is a compact subgroup of IM. Okay. This is a very interesting thing. Okay. Now this happens for this for a Riemannian manifold, and now we want to go to a Riemannian symmetric space. Okay. So Riemannian symmetric space, IM is the Lie group.
So this compactness of this stabilizer will come from that singleton set is compact, right? Is it so?
Singleton set is actually at present I do not remember the proof. So probably I do not know. I am not saying anything about it. So
Okay.
simply I do not know this thing. So now we really come to this symmetric space theorem. So let M be a Riemannian symmetric space. Then IM okay, equipped with compact opponent topology has a smooth structure on M, but that has to be unique. I have explained in the beginning that because has a unique smooth structure on its structure, STRUCT structure on it, so that IM acts as a
One
yes sir.
smoothly surface.
Oh yeah, thanks. As a unit on with structure it on so that IM acts a so this is a Riemannian symmetric space. So therefore this we have shown that IM acts on M transitively. Acts as a IM acts a transitive Lie transformation group of M. So now in this case, actually, since this has IM is second countable, so in this case, if okay, this so it is not required, but let us say let P belongs to M, K tilde is equal to really G belongs to G so that G dot P is equal to P, then alpha from IM to K tilde to this M is a diffeomorphism. Given by alpha G dot Cp to G dot K to G dot P is a diffeomorphism. Yeah, so for proof, you can see Helgason, and the proof is also not difficult. But the thing is, okay. One thing actually here it is also true that if M is only Riemannian manifold, then IM is also Lie group, but the proof is difficult. And here there is only advantage that IM acts on M transitively, and that somehow really makes the proof easier. Okay, so you can. I could have done it, but it will simply take 2-3 classes, and which I do not like. So now I want to prove a proposition. So let G be a transitively transformation group of a connected smooth manifold M. Manifold M. So let P belongs to M, and this GP is really G belongs to G, so that G dot P is equal to P. This is stabilizer of P in G. Assume that alpha from G mod GP to M is given by this thing. Alpha G dot GP to G dot P is homeomorphism. Then this G naught is the connected component of identity in G. This acts transitively on M. See, the thing is, we are assuming that M is connected, and this G acts transitively on M, and alpha is a homeomorphism. Means eventually alpha is a diffeomorphism. So we will use this thing, and I will prove this thing. So proof is very. So proof. So let pi from G to G mod GP be the projection map given by this thing. Pi of G is really GGP. So pi is a projection map, so therefore and it is continuous and open map. So we know that this pi from pi is a continuous open map. Projection map is really open always. If you do not know this result, then you can take it an exercise. If you do not know this thing, and so this we have this map from G to G mod GP, and this is really your pi, and there is some map alpha to G mod GP to M. See, this is really this goes to G going to where G dot GP, G going to G dot GP, and this maps to where this map to G dot P. Okay. Now pi is open map. This is open map. Now alpha is a homeomorphism, so therefore alpha is also an open map. So alpha is open since alpha is homeomorphism. Okay, so I am not writing this. So alpha is open. So therefore composition. So since both pi and alpha are open, this composition or this beta, so this is alpha composition pi from G to N given by this beta of G is equal to G dot P is an open one. Okay, so that is the thing. Now you take this. We also know that G naught. Actually, if you look at if G is a Lie group, if you look at the connected component of identity, that becomes a both open and closed subgroup of the Lie group. We also know that G naught is a G naught is both open and closed subgroup of G. Okay, so this is also a standard, and this happens in case of a Lie group. Okay, so it may not be true for this so-called any topological group. For instance, Q. If you take Q, then this what is the connected component of identity? This is just 0. So that is not really open. So this is not really true. So so we also know that G0 naught is both open and closed. So thus we get this. So G is equal to really G naught. Okay, so union of some G naught xi where I belongs to I. And what is this? This is the decomposition of G into right cotes. This is really decomposition of G into right cosets of G. So this is clear, because if you take this something like H, G, H is a subgroup of G, then G you can write something like Hx, X belongs to G. This is just, I am writing this G as a right coset of G naught. Okay. Now, thus we get G dot P. This is equal to union I belongs to I, G naught xi dot P. But since this action is transitive, so G dot P is whole M. So M is equal to I belongs to I, G naught xi dot P. So as G acts on an M transitively. Okay. Now, since okay, G naught is open in G, so therefore, if you translate something, that will also open in. Since G naught xi is open on G, and beta is an open map. This G naught xi dot P, this really what this is really beta of G naught xi. Sorry. Beta of G naught xi. This is open in M, and this is for happens for each I belongs to. Okay, so each G naught xi dot P is open in M. So now observe that so G naught xi dot P is the orbit of xi dot P under the action of G naught. Okay. So this this was okay. So G naught X. This is clear because okay. So this is clear because simply you G naught Xi dot P is something like G naught Xi dot P. This is from the group action property. So you know that if you group arcs on some space, either two orbits are same or they're distant. If they intersect, then they has to be same. So therefore, this G naught Xi dot P. Therefore, either okay. G naught Xi dot P is equal to G naught Xj dot P or G naught Xi dot P intersection G naught Xj dot P. This is really pi for Ij belongs to I. Now we have this thing. We have M is equal to really union of I belongs to I. This is your G0 Xi dot P. So since these are the distant or same, therefore I can write this as distant union. So this is I belongs to some I tilde, where I tilde may be subset of I. This is equal to G0 Xi dot P. And each G0 Xi dot P is open. Okay. Now, thus I get this G0 Xi dot P is really M minus this is disjoint union J belongs to I tilde and I not equal to J, this G0 Xj dot P. Okay, so here I am taking from I tilde. Now since each G0 Xj dot P is open, therefore G0 Xj dot P is also closed. Since G0 X dot P is open in M for each G or each J belongs to I tilde, therefore G0 Xi dot P is really closed. Okay, this happens for any I belongs to I tilde. So now as M is connected, therefore I tilde has to be singleton. Okay. And M is equal to G0 Xi dot P. So, as M is connected, therefore M is equal to really I have a I tilde is singleton and M is equal to G0 Xi dot P. So this so that thus G0 acts. So thus G0 acts transitively on M. So is it clear, Mithunda?
Yes, Mona.
Bhavna, it is clear, Bhavna? She is not here. Riju?
Yes, Mona.
Okay, so this is the thing. So we want to apply this theorem for this Riemannian symmetric setup, and for Riemannian symmetric space, IM really acts transitively on M, and everything holds everything is actually is satisfied. So okay, so this is really so proposition. So let M be a RSS So let I am not be the connected component of identity in IAM. So then I am not really acts transitively on it. So this is proof is clear from the since I am acts transitively on M. This is clear from the previous proposition. Transitively on M, therefore the proof is clear from previous proposition. Okay. So that is a thing. Now actually what I will do, I will really actually prove this proposition in a different way. This was the proof which really Helgason gives the thing in his book. But there is another proof, and this is also nice, and that is there in that note, second note, Alexandra IOG or something like that. So, so let us give another way. This way. So, another proof. So let this psi is a mapping from M cross M to IM with the map given by this thing. Psi of P comma Q is equal to really SP composition SQ. Okay. So this is the composition of two isometry. So it can be shown that this psi is continuous. So I am not really why this is continuous. I am not giving the rigorous proof, and I am also leaving this proof because the thing is one has to really go into the structure of this IM to show this thing if you want to be rigorous thing. But if you really
one of these
hello, sir?
SQs are geodesic reversing isometry, isn't it?
Yes, sir. Yes, sir. So since SP and SQs are some geodesic inversion around a point P is okay. So if you change perturb little bit P, then geodesic inversion actually will we will change the isometry by little actually in the compact opponent topology, of course. So so this is the thing. Therefore, this is really not hard. Means you can believe that this is continuous. Okay. So I am not really giving the rigorous proof, but this is continuous. Okay. So observe that this psi of P comma P. Really, this is really SP composition SP. This is really SP square. This is identity. Now, since this M cross M is connected because M is connected by Riemannian manifold. Is connected and psi is continuous. Therefore, this psi of M comma M, okay, psi of M comma M cross M will lie inside a connected component of this IM. Okay, and also we know that psi of PP is identity. So let us add this thing. And since M cross M is connected and psi is continuous and psi of P comma P is identity, therefore, so this implies psi of M comma M cross M. This is lie inside the IM naught. So this so that thus okay this so that for any P comma Q belongs to M, this psi SP composition SQ, this belongs to IM naught. Okay. So for any PQ belongs to M, so SP composition is SQ belongs to M naught. Okay, so now let take any arbitrary point PQ belongs to M. So let PQ belongs to M, and let gamma be a geodesic joining P and Q. Let gamma A comma B be a geodesic in M joining this. Gamma of A is equal to really P and Q. Okay, and gamma of P is equal to Q. Okay. So this is my picture. This is my say. This is my P. This is my Q, and this let M be the midpoint of this geodesic gamma. So let M is equal to gamma A plus B by 2 with the midpoint of the geodesic. So joining with the midpoint of the geodesic gamma, simply right. Okay, so since I actually SM is the, if you look at this SM is the geodesic inversion about the point M. Therefore, okay, so clearly this, therefore what will clearly this SM of P is really Q, because simply SM is the geodesic inversion about M P. The SMP is called Q. Now you apply this to both hand side to apply both hand side to SQ. So SQ SMP is really SQQ, and this is Q. So that means, and we have seen that SQ SM belongs to IM naught. Okay, since SQ composition SM belongs to IM naught, therefore thus this IM naught acts transitively on M. So this is the second proof. This proof is also nice according to me. Now, Ushab, this proof is clear.
Yes.
As actually, I forgot to state one proposition that will be useful for us. So, which is in the setup of Riemannian manifold. So let M be a Riemannian manifold. So this is not a symmetric space. Okay. N manifold. Then let Fn this n belongs to n be a sequence in IM. Okay, so then this okay, then this Fn converges to F in compact open topology. If and only if so Fn x converges to Fx for every x belongs to n. So this says that the compact open topology on IM is really is same as the topology of point-wise convergence on IM. So and actually, if you there is also another topology that uniform convergence on compact set. That topology also same with these two topology. So and for proof you can see algorithm. Okay. So remark.
This is only true for Riemannian manifold or true for any topological
Actually,
space?
Helgason has proved this for Riemannian manifold. But this is true for any matrix space also. Actually, Cowling, I was attending a talk by Cowling, and there he mentioned that in IM also you can define this isometry. Simply this you just define isometry that those maps which preserves distance and bijective. And he where
Decreases distance, preserve distance.
preserves distance and bijective. I from M to M is on to I up to also as well. And preserves distance. I mean that is isometry, right? So in that you give this compact topology and this so-called point-wise convergence topology and uniform convergence on compact set topology. Then these three topologies are coincide. Actually,
Just
but
let me see the statement again. Scroll down.
Okay, I am writing this thing. If I know Fnx converges to Fx for every x vector. Is it okay?
Yeah, fine.
Okay, so let me put that remark. So let M be a Riemannian manifold. So remark manifold and this then three natural topologies on IM. Topologies in IM, namely this first is really compact open topology. Second thing, topology of a point-wise convergence. Third is really topology of uniform convergence on compact set. Uniform convergence coincide on IM. So these are same topology in fact. So, but this proof you can find in Helgason proposition. I have also read that proof. So, corollary is corollary if you this evaluation map. So let M be a Riemannian manifold. This then this E map evaluation of P from IM to M given by this thing. This EPF is equal to really FP is continuous. This is clear, right, from this previous proposition? Because if because if this Fn converges to really F in compact topology, then simply this Fnp will converge to Fp. So therefore this is really clear. The evaluation map from IM to M is continuous. Okay, so now we want to important discussion. So this section is extremely important. So really pay some attention because we are going to this so-called Lie theoretic characterization of symmetric space. So let M be a RSS, Riemannian symmetric space. Let G is equal to really IM naught with the connected component of identity in IM. in IM. So let P belongs to M be fixed. I will fix this base point always. So delta P belongs to M belongs to M. And K tilde, really this G belongs to IM. So that G dot P is really P. Okay, so we know that this K tilde is compact. This K tilde is compact. This is stable. Okay. So now, so let K is equal to really the G belongs to G, so that G dot P is equal to P. This is a stabilizer of P inside G. This is G. What is G? G is IM naught. Okay, G is the connect. This is stabilizer of P inside G, and this is really what G intersection K tilde. Okay. Now since this G is really closed in IM, therefore this K, this is G intersection K tilde is closed in K tilde. Okay. Now as K tilde is compact, therefore this implies K, and since K is closed in K tilde, and K is closed in K tilde, this implies K is compact. So this implies K is compact. Now this since if we have already stated that proposition that IM is second countable, therefore its connected component will also be second countable. So since IM has countable base, therefore this implies G has countable base because G is the connected component of IM. Now another thing, but okay. So we also know that IM acts on M smoothly because of that theorem which I have stated. Therefore, G also acts on M as smoothly, and we have just proved that G acts on M transitively. Therefore, since G acts on M transitively, therefore G is a transitive Lie transformation group of M. Okay, group of M. Now this thing is and this map alpha from G mod K to M defined by alpha of Gk is really G dot P is a diffeomorphism because so this is the thing. Now okay, so this I have really proved that therefore G mod K is really diffeomorphic to M. Okay, so this is now we really define this sigma from IM to IM. Okay, let's see. So let sigma from IM. Okay, so let us use the first space. So now that's okay. So let sigma from IM to IM be the map sigma of G is equal to really SP G SP. Okay. So we know that this SP square is equal to identity. Therefore, SP inverse is equal to SP. SP is equal to SP inverse. And this is really a conjugation by SP. Okay. And this is a group isomorphism, and this is really inner automorphism. Okay, and since sp square is identity, therefore sigma square is also identity. So okay, so what I'm saying that sigma is an automorphism of the group IM because this sp is equal to sp inverse, and this since
So
this
how do you
IM
get
is a
sigma
loop.
square to be identity?
Okay, so I will do that. So this just compose two times, right? Okay.
Yes, so SP, then SP square is identity, but G will
Okay, so,
come, right?
okay,
Somehow.
just wait. Okay, so
Post multiply and pre multiply by SP. That will do.
yeah, so do you get it? Clearly, sigma is a smooth automorphism of the group IM with sigma square is equal to real identity. Okay. What is sigma for? Okay. The sigma square G is equal to sigma G. Sigma of G is really SP sigma G SP, and this is SP sigma G is SP G SP SP. So this is SP square G SP square. SP square is identity. This is G. Sigma square is identity. So did you? So are you convinced, Manoj?
Yeah, sorry.
No, so you should not say sorry. Okay. So clear sigma is a smooth automorphism of the group IM with sigma square identity. But since sigma is a really continuous map, and so it maps, and this is a really group homomorphism, then it maps identity to identity. Therefore, sigma will map the connected component to connected component. Okay, and since sigma is equal to sigma inverse, and sigma is continuous group homomorphism. Therefore, sigma G is equal to G. Okay. Thus, sigma from G to G is a group automorphism of a smooth group automorphism. Actually, smooth you should group automorphism of G with sigma square is identity. Claim this sigma is an involution. Okay, so claim sigma is not equal to identity. Sigma is not equal to identity. Suppose sigma is equal to identity. That means sigma G is equal to G for every G belongs to G. Okay. That means SP is equal to really G for every G belongs to G. That means really if you act this on a P, this G of P, but since SPP is equal to P, then you can write it in terms of group as an SP G dot P is equal to G dot P. Now as G acts on a transitively, therefore thus we get this SP is equal to identity, which is a contradiction because SP is strictly an inversion. So which is a contradiction. Okay. And hence, and these types of maps where sigma is not identity but sigma square identity, these are called involution, and sigma is an involutive automorphism of the group G.
Mona, I have a question here. This I don't know. That
Yes, sir.
The question is, we know that SP has a fixed point, that is T. Does it follow that if it has more than one fixed point, then it is identity?
No.
Okay.
More than one fixed point. SP P is the isolated fixed point of SP.
No, but it
P
can
is an
have more.
isolated. Actually, you have missed that class actually.
Okay.
So in fact I will use this fact. Okay.
Okay.
I think it was an 17 lecture or something. So let us. Okay. So for instance, this sphere. Actually, I have given you, sir, this example. This sphere as SP. If you take this SP, this has more than one fixed point.
Yes, that's correct. Correct. Yes, I
But
was.
this is an isolated fixed point in a
Yeah, this is
neighborhood.
one. Right. I remember now. Correct.
Actually, this lecture 7. You have missed that class. Actually, I know that.
No, I was there. I remember.
No. This example you are there, but where you have proved that SP is the isolated fixed point. The proof when I presented that proof, then you are not there. Okay. So let this G sigma is equal to really G belongs to G, so that sigma G is equal to G. This is a really set of all fixed point of sigma. Got set of all fixed point of sigma, and this clearly this since sigma is continuous, clearly G sigma is a closed subgroup of G. Therefore, this G sigma is also a Lie group. Thus, G sigma is a Lie subgroup of closed Lie subgroup of G because by of Cartan's theorem. So this is subgroup G by Cartan's theorem. Now also let this G sigma naught with the connected component of identity. Component of identity in G sigma. Okay, so in G sigma, and this G sigma naught is also closed in G sigma. Therefore, this is a closely subgroup. This is also a Lie group. Thus, G sigma naught is also a closely subgroup of G's. Subgroup of G. This is clear. So now there is an interesting claim. I want to really prove that. Claim this G sigma naught is contained inside K. This is contained inside sigma. Okay, so okay, so this is I have to really prove. So first I am taking this thing. Okay, so first I am taking this K subset of G sigma. So are you able to hear me? Or there is some problem?
Yes, I can.
Okay, there is some sound is there, so therefore I am really so GSP KSP. If you take this thing, this is really DSPP, DKP, and this DSPP, and this is really DSPP is this minus identity, right? Because and this is really dkp, and this is minus identity. Okay, so this is really dkp. So and this is really kp. So k, both k and sp ksp are two isometries. These are same value at a given point p and same differential. Therefore, by rigidity of isometry, okay, rigidity of isometry, we get this this SPK is really k. So this is really sigma of k is equal to k. Okay, so thus I get this k is really inside this G sigma. Now I have proved okay, so really. So I have proved this one part, and second part I have to prove. But second part, as I said that I have proved this theorem that P is the isolated fixed point of SP. Okay, see this is in the lecture 17, I guess.
You have proved
Just
that
wait,
that is an isolated fixed
okay,
point.
just let us show that statement to screen. Yeah. So proposition, let M be a Riemannian manifold, then following are equivalent. M is Riemannian symmetric set, and each P belongs to M is an isolated fixed point and involutive isometry SP of M. So you will use this proposition, okay? So, so let this V is equal to really okay. So let N be a neighborhood of P in M, so that this the only fixed point of SP in N is really is P. Okay, so I have to this is possible. Okay, so N be a neighborhood of P in N, so that the only fixed point of SP in N is P. So I look at this thing. Let this B is equal to this G belongs to G sigma, so that G dot P is belongs to N, and B N is a neighborhood of open neighborhood of P. So N be a open neighborhood. Let us write this is open neighborhood. Okay. So neighborhood of so since this so B is equal to G belongs to G sigma, so that G dot P belongs to N. Since this thing G going to G dot P is continuous now. It's a continuous map from this IM to M. Therefore, this B is an open neighborhood of okay, B is an open neighborhood identity. So okay, E in G sigma. So here actually it is clear that E belongs to G. Clearly, this identity belongs to B, because N is in neighborhood of P. So clearly E belongs to B. So since G going to G dot P is continuous map from IM to M, therefore B is an open neighborhood of P in G sigma. Okay, so let G belongs to this B. So and the B is by definition this is subset of G sigma. Therefore, sigma G is equal to G. Now this is really sigma G is really SP G SP is equal to G, and I apply on this P. SPG SP of P is really G of P. So that gives you this, since SPP is equal to P, this SP of G dot P is equal to G dot P. But G dot P belongs to N. Okay, since only fixed point of SP in N is, okay, P is the only fixed point of SP in N. Fixed point of SP in N. Therefore, we get this G dot P belongs to, okay, G dot P is really P. Okay, so this implies G belongs to really K. So what I am getting, this I have chosen an element G belongs to B, and I am showing that that is an element of K. So this really B is subset of K, and this, what is this P? This is an open neighborhood of E in G sigma. If you let G be a Lie group, and if you take any open neighborhood of a Lie group, that will generate the connected component. Okay, so this implies G sigma naught is really K. That is really because I am using this fact that any neighborhood of identity in a Lie group, say H, generates the connected component. So thus we get this thing. Thus we get this thing that G sigma naught really K inside G. Okay, so now let us write everything in a theorem. So thus we get the following theorem. Thus by previous discussion, okay, so I am already discussed. So we get the following theorem. So theorem, this is an important theorem. So let M be a RSS. Okay, so let P belongs to M. Oh shit. See, I better to use a place space. Theorem. So let M be a RSS. Let P belongs to M and G belongs to G is equal to I am not. Let K is equal to G belongs to G, so that G dot P is equal to P. Then this then K is compact, and G acts as a transitive Lie transformation group of N. So that alpha from G mod K to M given by alpha GK is really G dot P is a diffeomorphism. So this is second part. The map sigma from G to G defined by sigma of G is really SP GSP is an involutive automorphism of G so that this G sigma naught contained inside K contained inside G sigma where this G sigma is the sigma is the G belongs to G so that sigma G is equal to G and G sigma naught is the connected component of identity in G sigma. So this is really this is what I wanted to prove, and this is a very important theorem. And tomorrow, and derivative of sigma is called Cartan-Ball solution. Tomorrow we'll in the next lecture we will define that, and slowly we will really we will move towards the Lie theoretic characterization of Riemannian symmetric space. So in the next lecture I will define something called Riemannian symmetric pair, and we will study that in more later. So we have really finished two sections. The first thing, classical degree, and Riemannian symmetric space definition and generality, and from the next session we will pick up Riemannian symmetric pair. So with this I would like to stop, and if there is any question you can ask me. Tapendu, Riju, Pritam.
So far we understand that the Riemannian symmetric space is of the form G by K, and G is that kind of a neighborhood where there is a map like sigma. Unless G
Yes,
has any
yes.
map like sigma, it cannot give rise to a Riemannian symmetric space.
Sir, actually I could not hear the last line properly. Sir,
I'm
could
saying
you please repeat?
has a map like sigma,
Yes.
it cannot give rise to a Riemannian symmetric space.
Yes, yeah, that is what you will see. So today somebody is doing recording, or today nobody is doing recording? Oh my God! Today Pritam is supposed. Pritam, are you there? Huh?
Yeah, it's recorded.
Hello?
Pritam
Pritam da is recording. Okay.
yes.
Okay. So we will meet then in next lecture. I am so disconnecting this.